class today. Hey, good morning. In case you are not aware, today we're gonna work with the Ample software. So if you don't have the software installed in your machine, you can pick up one of those laptops. I posted the slides over the weekend, but again, I was not expecting you to have the software downloaded, so those machines should have access to the software. So the plan is that we're gonna lecture for about an hour, and then I have the exams with me. So I'm gonna pass the papers back, and we're gonna discuss the exam. So we're gonna do that by 10:30. And as we started last week, the discussion on how to solve problems using computers, we spent our last lecture discussing how to build models using Excel, Microsoft Excel, and how to use the Excel solver to solve those problems. And as part of our discussion, we talk about the limitations in terms of capacity for Microsoft Excel. So with the solver adding that is provided by Excel, you can solve problems that has about 200 variables, 200 decision variables. I also talk about the solver adding called OpenSolver, and I posted the link there to. So if in the future you need to solve problems that are larger than 200 variables or have more than 200 decision variables, you can download the OpenSolver adding and use that to build and solve larger models in Excel. So for the problems or for the problem that was assigned for the lab, you can solve that with the Excel solver. You don't need the open adding. You don't need the OpenSolver adding. That link is there for reference. So in the future, if you need it, you know where to find it. So today we're going to transition to a different software. This is a commercially available software called Ample, and this is another tool for your toolbox in terms of solving linear programming and other type of optimization problems in the future. So the good thing about Ample is that it makes easier the build of the actual model, the setup of the model. So if you know how to use Ample, you can easily describe or code your model into this software, and you will be able to solve the problem without issues really quick. The other good thing about this software is that you can reuse your models. And you'll see what I mean by that. If you're able to code your model in the right way, you will have that as a separate file, and then you can create a data file in which you can create you can update that data file as many times as you want, and then use the same model file to solve that problem. So the lecture today is called Solving LP Problems Using Computers. And today we're going to focus on using this new software called Ample. So the definitions, I have algebraic modern languages. They are high-level programming languages with which one can specify and solve optimization problems. So there's two things that you will observe when you use Ample. Ample by itself is the interface between the decision maker or the programmer and the solver. The Ample interface basically is the one that translates your model into a language that the solver can understand and you can solve after that. So these high-level programming languages, they are continuously being updated as research is performed. You'll see more people building more efficient or faster algorithms, and you will see that this commercially available software will pick up those new algorithms and will implement those within their interface. So there's a lot of them have updates coming up every year because they're continuously updating to keep up with the advancements in the field. So as I mentioned, these languages do not solve the problems directly, but rather invoke algorithms or solvers to obtain a solution. Some languages have the advantage of having a syntax similar to the mathematical notation used to describe the optimization problems. So I have a list of commercially available softwares here. You can search by yourself on Google. You'll find their webpage. But today we're going to focus on Ample. This Ample is one of the software that is mostly widely used in industry and also in research. So that's why we are going to focus on it. So Ample is a mathematical programming language. The user interface is a terminal for input of command lines, and it is reached by running the command ample.exe. We also have an interface now. It's built in Eclipse, and that's the interface that we're going to be using. But when I was an undergrad and when I was a graduate student, you were basically running Ample from the iOS. So you were using this black window to code and to solve the problems. But now we have this nice interface that is very helpful. The files contain the model, data, configurations, and other programming structures that can be edited by a regular editor. And there exists a developing interface, the Ample IDE, which facilitates the editing and execution of Ample commands. So here's some information if you want to download the student version of the software. You can follow these instructions. Here you can go to this link. If you download the slides, you can click on that green link and it will take you to this window. If you have a Windows computer, you follow the instructions to the left. If you have a Mac, you follow the instructions to the right. If you have a 32-bit computer, you have the zip file for 32-bit, and if you have a 64-bit computer, you follow the instructions for the 64-bit. If you don't have the software installed today, if you're here in class, you can use one of the laptop computers that we have available. Here, if you're at home, you will have to download the software and work from your computer. So let's talk about building models in Ample. So the basic files, we have three basic files, the .mod. This one is used to declare the elements of the models. So for example, the variables, the objective function, the constraints, and data. sets and parameters. So basically what you do in the .mod is to define your formulation. So decision variables, parameters, objective function constraints, and also the bounds for your decision variables. In the .bat, it is used to define the data for the model. So in this one, you basically put all the information, like the cost associated with each decision variable, the right-hand side values for your constraints, the parameters associated with the problem itself. And then the .run, it is used to run your program. So here's where you state the instructions. So if you want to print, if you want to solve, if you want to write a file, all that associated with the solution and solving the problem, then you use the .run file. And I will show you an example how that looks today. So starting with the MOD file, here's some syntax that you need to be aware of in terms of how to define your model. So we have a variable or var syntax that we use to define the decision variables. For the objective function, we need to specify whether you are minimizing or maximizing. So for minimization, you use minimize. For maximization, you use maximize. And then you have to provide a name for your objective function. So if you're looking at cost, you can call this the objective function cost, and then you're going to minimize cost. If you want to call it something else like objective function, you're going to minimize objective function. But you have to provide a name because the software will refer to the objective function based on the name that you provide for the objective function. Same thing for the constraints. So each constraint will have a name associated with it. If you want to make things easier for you, you can just say C1, C2, C3, but you have a different name for each one of the constraints. And this will apply for every constraint in your model. Some remarks: every line instruction must be terminated with this semicolon. Line comments are preceded by symbol. So if you want to make comments in your code and you don't want that to take as an instruction for your model, you can use this number symbol in front of that line, and it will make a comment for your code. Block commands are enclosed by the symbols, these dash tags. And ample is case sensitive. So if you are using capital letters for defining things, you have to use capital letters to code and so on. So case sensitive, and variable names must be unique. So every decision variable should have a specific and unique name. So here we have an example. We're going to start very simple. The problem description is Paint Deals produces two colors of paint, blue and black. Blue paint is sold for $10 per liter, but black paint is sold for $15 per liter. The company owns a process plant which can produce one color paint at a time. However, blue paint is produced at a rate of 40 liters per hour, while production rate for black paint is 30 liters per hour. Besides the marketing department estimates that at most 860 liters of black paint and 1,000 liters of blue paints can be sold in the market. During a week, the plant can operate for 40 hours and the paint can be stored for the following week. Determine how many liters of each paint should be produced to maximize the week revenue. Okay, so a very similar problem in terms of production planning. We have seen this type of problem before. So if we were to formulate this, we have two decision variables, one for how many blue paint liters you're going to produce, and then one for black paint. And then we have a constraint that is set up. If you remember that truck problem that we discussed in class, that we are trying to find the fraction of how many of each product we're gonna use to cover the capacity, and then we have the demand constraints. So this is the basic structure for the MOD files in AMPO. We have first, and you see those in green, those are comments. Those are not part of your code. These are here just to provide additional information. So the first part in your code is to declare the variables. So as you can see, we have two variables, and each one of them has a unique name. So we have blue paint and black paint. And then we have an objective function. This is the second comment, part 2. You see the name maximize, the name of the objective function, you're maximizing revenue. And then you are using the definition that you made for the decision variables to define your objective function. So 10 is the profit or the revenue for blue paint, 15 is the revenue for black paint. And then part 3 are the constraints. So our constraint in terms of time is 1/40 times the decision variable blue paint plus 1/30 times the decision variable black paint. All that less than or equal to 40. And then we have the limitations for the demand for blue limit and black limit. And very simple. A couple of things to remember. You end each one of these declarations with a semicolon. And also when you define your names, you're gonna have to use these dots for the software to understand that this is the name of the constraint for the objective function. The run file, here's where you state how are you gonna run this file. So example1.mod is the name of this file. So we are calling that, we're gonna start our run file with resetting the software. We don't want to keep any decision variables, definitions, or values stored in the memory. We want to reset everything before we run the problem. So we reset, and then we call the model that we are trying to solve, and then we call the solver that we're gonna use. So in this case, we're gonna be calling the solver Cplex. There are many solvers, each one of them. So AMPO again is the interface that is building your model, and then once AMPO build that model, is gonna call a solver to solve the problem. So there are many solvers out there. One of them is Cplex. So we're gonna call Cplex. And after stating the solver that we're gonna use, we're gonna make this instruction solve, and that should give you the solution of the problem. And then these instructions right here are basically stating that you want to see the value for the decision variables blue paint and black paint after solving the problem. You also want to display the solution or the objective function value, which name is revenue. And also you want to see the solution time. I'm sorry, the constraint. You want to expand the values for the constraint time. So let's try to code this in AMPO. So how many of you have access? You have computer, you have it in your computer, you have it in your computer. So I'm going to show you the interface. Okay, so to access AMPO, you have this icon with the black hat. That's the icon for AMPO. So you double click, or you can just search on in here for Ample, and you should at least get a directory. So if you click there, you will have the shortcut here. So if you don't have it in your desktop, you will find it in the Ample folder. You can double click there and it should take you to this window. Okay, so in this window, what you have is the directory. You have to search for the folder in which you're saving your problem models or your files for the problem. So for example, right now I haven't created those files yet, but I have a folder in my desktop called Ample. So there's where I'm going to be saving my files. So when I open the interface, I search for that desktop. I go to my desktop and I find the folder Ample, and inside that folder I have a folder for this class. So I click there, and that's going to be my my directory for the software. So the files that I'm going to be using to solve the problems are going to be stored there. The other thing that you have is the console. So here's where we're going to be typing the instructions for Ample. And if you click on one of these files, you'll see that the software will open the content of the file on this window. So here's where you're going to be coding the model. So that's essentially it. You have these three windows: location of the files, the console when you're going to type the instructions for the software, and then this one, which is basically when you double click the file, you can code on that. You can code the file in this window. Okay, so let's work with the problem. So typically, no, those are, I created those already. We're gonna create the model that I just discussed together. Those, I created those beforehand, so that's why those are available. They're stored in this folder. You don't have them yet, no. What we are going to do is, once you create so there's two ways for creating new files. So I'm going to go up here. So this is the folder that I'm going to use. So you can go to File, New File, and create a file. And when you go there, you can type the name. Let's call this example 1. And then you select the type of file that you want to create. So .mod, .dat, or .run. So this is going to be a example 1 .mod. And typically, that's the option that is provided by the software. But sometimes what I find is when I go this way, the software will freeze for some reason. Let me see if that's the case now. No, it worked well. So once I create this, you'll see the file. You'll see the file here, example.mod. And the file right now is empty. And I have the console, everything set up for me to start coding. Any questions? You created a file? Yes.
How do I get that window on the bottom left?
The current directory?
Yeah.
It's not showing up for you?
Yeah, because
I think if you go to window, it should show the, let's see. No. Okay, so you don't see it?
All of them are. So, folder somewhere. Be covered. Radio, freezing. Now you go to file. File. Go put it. So,
Okay. So let's move on. So now you have the editor here. So essentially what we're gonna do is just recreate that file that we have here in this window. So we're gonna type this. You don't have to type the comments. You can start with the variable definition. So we have blue paint. And then the other variable is black paint. So those are the decision variables for this problem. And then we're going to type the objective function, which is maximize revenue. And the objective function is the revenue for blue paint, which is 10, multiplied by the decision variable blue paint, plus the revenue for black paint. So 15 times black paint. And then use the semicolon to complete that statement, and then go to the next line. We're gonna do the constraints now. So the constraints use this code subject to, that's what's going to define the constraints. And we have to provide a name for that constraint. So for our constraint, we're gonna name this constraint time, and we're gonna use this two dots to state the equation now. So it's 1/40 multiplied by blue paint plus 1/30 multiplied by black paint. All that less than or equal to 40. And then we have the demand. So subject to blue limit. Zero less than or equal to blue paint. Less than or equal to 1000. And then subject to black limit. Zero less than or equal to black paint less than or equal to A60. Okay. So those are the code lines. The rest was in green in the slide. Those are comments. If you want to include those in your file, that's fine, but those are not going to impact the code. And then you can save. So what we have here is the model. Okay. Now we're going to create a second file that is going to allow us to solve this problem. And that's the .run file or run file. Okay, so we are going to create that file now. Yes. So if you are ahead, you can start typing the .run file. Basically, what you're going to do is you're going to create a new file. And instead of using the extension .mod, you're going to use the extension .run. Okay, so let's do that. We're going to go back to file. I'm sorry.
So did it save this?
Yes, you can. Every time you complete the code, you go to the floppy disk icon, and you click that, and it will save the file for you. Okay, so we're going to create a new file, and I'm going to call it the same thing, example1. But the extension is going to be .run. and then click finish. And that will open a new window for you to enter the code. You see the tabs at the top. One is for .mod, which is where the model is. And then we have example1.run. This is the new file. So here's where we're going to code the running file. So we're going to call this file to run and solve the model. So we start by resetting the memory. So this is the first instruction we want to make sure we include here. If we don't do that, there will be some information and data being stored in the model, and that can affect your actual solution. So we want to reset. We don't want to keep any values in the memory. We want to clear that so we can solve the model with an empty memory. So we do the reset, and then we call the model. This is the model that I'm going to solve. Example1.mod. So this is the name of the file where the model is coded. And then I'm going to call the solver. This is option solver Cplex. And then after calling the software that I want to use, I'm going to solve the problem. And then the next three instructions are basically there to display the solution values for the decision variables and for the objective function. So this is the display the decision variables, blue paint and black paint. Also display the revenue and expand the constraint time. And then click save. You want to make sure that you save before you do the instructions to solve the problem, which we're going to do now. And then what we're going to do to solve the problem is that we're going to call that run file by using the instruction include example1.run and then the semicolon. And when we do that, we'll get the optimal solution for the problem in the window. So this is telling us that the optimal solution is $17,433. And we should we should produce 453.33 blue paint and 860 black paint liters. And then the expand time, this is the constraint that we developed for time. So they're expanding this into the solution. So in case you want to see the constraint. Questions? Very simple, yes. Let me see. If we use the name of the decision variable, let me show you. You have to use a different name for the constraints. Okay, good. So in this problem, this is basic stuff, right? We define the model and we define the file to run to solve this model. But as you can see in this particular model, we have included the information for the cost or the revenue associated into the model, and we also include other parameters into the model. This is good practice if you're going to solve a problem that is small. But if you're solving a larger problem in which you're changing the data frequently, you don't want to include those parameters into the model. And the next example basically is teaching you how to split or how to separate the data from the model. And you call that data file when you're trying to solve the problem. So you can reuse your models and not being, so you don't have to go and type the new data inside the model every time you have to update that information. This is also helpful, like if you have an Excel file in which you can just run a code and the Excel file will output that file for you. And then you just pick up that file and put it into Ample and it will solve it for you. So you have many advantages splitting that information from the model. So let's go back to the slides. This is what I'm referring to here. Space settings. So this is another model. And as you can see in this one, it's also a production problem. The formulation is here, the top left of the slide. We have a set of products. We have a tons per hour of product J that is produced. B is the hours available at the mill. CJ is the profit per ton of product J. And UA is the maximum tons of product J for each J. So basically, if we define just the parameters in that way, when we set up the formulation, there's no numbers inside the formulation. You see, everything is defined in terms of the parameters that we define and the decision variables. Decision variables, Xj is the ton of product J to be made for each J. And so the objective function is to maximize the profit per ton of product J. And then that is going to be subject to this constraint that is similar to the one we used for the previous problem. And then we have the demand constraint, maximum ton of products for J. So this is a basic production model in algebraic form. So if we set up that model without the actual parameters values, you'll see that we're going to use those parameters that are given. So the model is to the right of the slide. We're defining the set P for the products. We don't know yet how many products we're going to have. We're just defining a set that is going to include those products. If this could be 2 products, 10 products, 100 products, doesn't matter for the file and for the model file, because this is defined in general terms. The parameter also dependent on the set of products. So B again is a set. We don't know how big the set is. We're going to define that in the data file. But P is the set of products. And then parameter B is the hours available in the mill. So that's part of the right-hand side of one of the constraints. Parameter C is the profit. And parameter U is the maximum ton. So that's for the demand. So we're going to use that also as a right-hand side of one of the constraints. And you will see now that the constraints and the objective function are defined in general terms without the parameters. So how do we set up the data? We're going to use a separate file that is called data. And here's where we're going to state the values for the model. So you see the set now P has the members of the set. In this case, we have two products, bands and coils. And then for each one of the set members, we are going to define the parameters. So parameter A for bands is 200, parameter C for bands is 25, and parameter U for bands is 6,000. For coils, we have parameter A 140, for coils, parameter C is 30, and for coils, parameter U is 4,000. Everything defined in this matrix form, but you have to be aware of the setup, right? So you want to make sure that you define the parameters, you state the name of the parameters that were defined here in the model, and then you put this sign right here that tells the model that you're defining the values for each member. So bands, 225 and 6,000, all located below those names. And then at the end, use your semicolon to say that the definition is completed. And then parameter B is by itself, is 40, and that's it. So the most important thing that I wanted you to get from this example is that now we are separating the data from the model. Again, if you have to solve that problem, basic production model using all the data, you don't have to touch that file because that is not going to change. The only thing that you're going to change is this. So if you have another problem that is going to use the same formulation, you go here, you say, okay, let's see if we have three products. You include another product into the set and you define these parameters for that third product, and then you solve it again. You don't have to edit that model file for anything. You just work with the data. And that's the benefit. And you will see that if you have to set up something like this in Excel, then you're gonna have to go and edit every cell and edit the interface for the solver. And it's gonna take you a lot of time. In this case, once you have this defined, if you want to add or change one parameter, you just go here, click something, add the information, and solve it again quickly. So that's one of the benefits of Ample. Okay, so I have created those files already. I knew that I was gonna get short of time, so that's why I had, let me post those on Canvas. Or if you, let's just go over them. So you see, same thing, we have the .mod file here. Total profit, time, and limit, those are the constraints. Something that you will notice that is different from the slides is that instead of using the parentheses, I'm using these symbols. I don't know if you can see that from there. Yeah, so that's it. That's something that changed. So you don't use the parentheses, which is what actually these are not parentheses. So this is right. So that's what you use. So if you use the parentheses instead of this symbol, you will get an error. So make sure that you use the those. And what else? This is the production. This is the data file. And this is the run file. So let me post these files in Canvas so you don't. I can't do this. Let me see. Have to go the long way. So those files are now available. In your modules. If I want to run that, I just have to go type include product run, click enter, and it will give me the solution. If I want to include the decision variables, XJ, so if you want to display the solution for the decision variables, you can go to the run and type display X. That will generate the solutions for bands and coils. So 6,000 bands, 1,400 coils as the solution. Yeah, so these are the, I mean, coding is the type of thing that you have to practice in order to get it. It's not, I mean, I can show you multiple examples, but it's not until you sit down and try to code these things by yourself that you are gonna see whether or not you are getting it. So that's why I created this lab 6. So you're gonna upload your solution, Ample and Excel file by the end of the day. And so I want you to try to solve the production planning using Ample on your own. And what I'm referring to is, if you go to lecture 3, all these problems are defined here. So production is this problem right here, production planning. So this is your data file right here. This is your data file. And you're gonna build a model using that data. And this is the formulation. So obviously, if you type in this into AMPL, this already have the data in it. Okay, so if you just go there and type this into AMPL, you will get the solution. But what I want you to try to do is to create this. Create the data files separately from the model and solve the model using that strategy. So try that. And then the multi-period production planning, what I'm stating here, I mean, as I'm saying, you can solve using Excel and also the bus scheduling. If you feel comfortable using AMPL and you want to use AMPL, go ahead and use AMPL. You don't have to go back to Excel. I'm giving you that option. In case you struggle with AMPL, you can try to solve it using Excel. Same thing for the bus scheduling problem. It is here. I'm sorry. Is this one. So you can use Excel or you can use AMPL to work with this one. I set up this to be due tonight. I think it's not enough time. So I'm going to extend this for a couple of days, see until Wednesday night. So if in case you have questions, we can talk about it on Wednesday. So you will have more time to work on this. But you have to try it. If you want to know if you are getting it, you have to try it on your own. Any questions? Yes.
Yeah, I just have one. For example, how would you set up a Slack?
You don't have to. It will generate it by itself automatically.
Okay.
So that's part of what the model does for you. So it will generate the Slack and it will solve the problem using the Slack because it uses the simplex method. Okay. So one more thing, since you're gonna be creating multiple files for this lab, when you get to uploading this into the assignment, I think it gives you the option to upload a single file. So go to lab 6 here. Let me extend this right now. So what you need to do, and I want to make sure that everybody knows how to do that, you're gonna have to create a folder and then create a zip file. Oh, you can do that?
Yeah.
Oh, okay, I didn't know that. I thought, okay, good. So if you can upload multiple files, that's fine. If you end up just creating too many files and you don't have enough space, you can create a zip file and upload the zip file. So everybody understand what the zip file is, right? Good. So let me extend this to Wednesday night. Yeah, more time, and then on Wednesday, if you have questions, we can clarify. And now we're going to talk about the exam. So I'm going to start passing the exams back. For the lab, it's just a single production problem. Yeah, the jacket, single production. And then for Excel, the multi period production problem and the bus scheduling problem. Okay, good, very good. Okay, so since nobody is connected, I'm gonna stop here.